We will conclude the multiplication counting principle lesson with pizza and 5-card poker problems. And we'll begin with our pizza parlor offering custom-made pizzas in 4 sizes and 6 different crusts. The pizza parlor also offers 14 different toppings to choose from, and just to make this a without replacement problem, they will not allow you to duplicate a topping on your pizza, so no double cheese for you. Now, if size and crust does not matter, I would like to figure out the greatest number of pizza possibilities in terms of combinations is with how many toppings. So I guess what I'm saying is, is there more ways to do 1-topping pizzas, 9-topping pizzas, 13-topping pizzas? Well, in the end, we've talked about this once before. If you want the most number of combinations, you're going to find it at the halfway point of the number of choices or / options. So if I take 14 and divide it by 2, I will come up with 7. So that is where I will find the most possibilities. And if I do 14C7 on the calculator, 14 math, come over here to probability, and C7, you will see that there are 3,432 different ways of having a 7-topping pizza, assuming no duplicates. So when I ask you how many ways you can have a 4-topping pizza, I would expect that number to be less than 3,432. And since the math for this is simply 14C4, I will just go ahead, second enter, change the 7 to a 4, and you will see that you can have 1,001 different ways to have a 4-topping pizza. Again, we're ignoring the size and the crust at this time. And the next question says, this is the same number of pizzas as having how many toppings other than 4? And what we're trying to get back to is, we've learned that if you take 14C4 minus 4, which in this case is 14C10, you will still have the same number of toppings as if you had 4 out of the 14. And for that reason is because if you choose 4, you leave 10 off. And so the answer to this question was 10. Now let's go ahead and add our size and crust options as well. And I would like to know how many 2-topping pizzas are there possible. So in some respects, we're going to do the multiplication counting principle because I'm going to need to determine the size. I'm also going to need to determine the crust. And then I'm going to need to determine the number of ways of doing 2 toppings. And for this particular problem, I know there are 4 sizes. Now what I want you to also know is I could have said this was 4C1. I could have also said 4P1, but you're going to see in a moment that there's going to be a kind of a general theme of constantly using C's because more times than not, it can be thought of as a group and not so much where order matters. So I'm going to now say there's 6 crusts, but I could have said that was actually, should have said 6C1. And then the 2 toppings, well, that one I'm going to need to figure out using combinations, since putting on, let's say, sausage and pepperoni doesn't really matter how I placed them on there traditionally. And I found out that there were 91 different ways to do that. And if I would type that all into the calculator and go 4 times 6 times, and then 14C2, which I have already predetermined is 91, we'll come up with that there were 2,184 different ways to have a 2-topping pizza if we can now alter our size and our crust. Now it also says this is the same number of pizzas as having how many toppings. And so this is just another variation of this question right here. So if I'm talking not having 2 toppings, then I guess I would want to go 14C, 14 minus 2, realizing that 14C12 should be the same as 14C2, and so I would want this to be 12 toppings. And just to kind of emphasize this, I know I didn't actually do 14C2 the last time, but let's just take a look here. 14, and then we'll come down here and we'll do the 14C2, and then I'll come back here and now do 14C12, and you'll notice I do get the same number. So yes, I did get the correct answer. So again, I'm trying to really emphasize that 14C12 is the same as 14C2, just like 14C10 is the same as 14C4. And so we come to the last question of our pizza problems, which is how many pizza possibilities are there total? Now what we're going to need is we're going to still need our sizes. We're going to still need our crust, all right? Then, well, this is where it gets interesting. I'm not sure how I want to name it, so I'm just going to think I'm going to keep it generic, toppings. And I'm going to put topping, yes, in parentheses, because this is supposed to include if I want 0 toppings. This will include if I just want 1 topping or 2 toppings. I might want my 4, I might want 7, heck, I might want 13. I could go all the way and have all 14 toppings. I want all the possibilities. Do I have to essentially work each one of those out individually? In a problem like this, you don't have to. I know that some students are going to think, well, you can't use the pizza toppings more than once, and we start with 14 toppings and work way down, and then they might use a factorial. That's actually not what's happening here. And in fact, you might think this was a without replacement problem, but you're going to find out actually it's a with replacement problem. And the reason for that is understanding what's actually going on. So let's take a look at each topping, okay? If they say, would you like sausage? All right, you might say yes. If they ask you, do you want pepperoni? You might say no. If they say, do you want onion? You might say no. If you want green pepper, they might say yes. What I'm trying to get at is there's only 2 options that are for each topping. Each topping has only 2 options. And those options are yes or no. And you can repeat them. This is a with replacement because if you say yes to one topping, that doesn't prevent you from saying yes to another topping. And if you recall, that means you would have to be going 2 for the first one, 2 for the second one, 2 for the third one, and you're going to keep doing this. So in the end, you're going to have 2 to the 14th topping possibilities because it's going to be a yes-no situation. We will still have our 4 sizes. Let's put that in blue. We will still have our 6 crusts, but there will be 2 to the 14th number of pizzas. And so if I type in that, 2 to the 14th types of ways that you could have toppings on your pizza, and you will find out that this pizza parlor can say they offer 393,216 different ways of having a pizza at their parlor. And so as we wrap up the pizza and move on to the poker, I want you to understand that that's kind of where these challenging problems are going to come into play here, because what we need to do is really analyze each situation before we do so. And I do enjoy teaching the 5-card poker, not because it's just a game, but it does kind of make you have to think hard how we're going to build a hand. Now, before we go any further, first off, let's figure out how many ways you can even have a 5-card poker hand. If you're not familiar with the game poker, let me just again explain that you're going to get 5 cards from the same standard deck of 52. The order of the cards does not matter, so how you're dealt, you probably will reshuffle them or reorganize them in your hand anyway, so that doesn't matter. We do have to watch out for that aces can be higher than kings, but can also be lower than 2s. They can't be both at the same time, but you can decide if you want to put that above or below. And so when you start analyzing, if you only have 52 cards, and you're only taking 5 of them, and order does not matter, and you've got to have different cards for your hand, you're not going to have as many hands as you think. And for those that are professional players, they know that there's only this many combinations. 2,598,960 different possible 5-card poker hands. What we're going to do is we're going to kind of go through some of the different types of hands that are out there. And we'll start with something that's called a flush. A flush is a 5-card of the same suit. So if I was deciding how I would build this particular hand, I guess what I would do is I would like to know what my suit is going to be. So I think what we should do is first determine the suit. Then we should determine, okay, the face values. Now, I'm not going to keep saying determine as I keep writing kind of out the steps for these type of problems. I just want to make sure that we understand. I think once I establish what the suit is, okay, I'm going to make a flush of hearts, then I would go ahead and choose the 5 face values of that. Now, there are some things that we want to watch out for, and that's why I'm going to bring up the straight flush right away. When I say flush, what we're going to do is we're going to talk about all possible flushes. That would include this flush that you see here, but I'm also talking about any flushes that might end up being straights. When you play poker, they're going to separate the straight flush and pull those out of the regular flushes. So straight flushes are going to be even in a more exclusive category because essentially they are the highest ranked hands. And then there's a special name for a flush called a royal flush, where you actually see ace, king, queen, jack, 10 in that order. When I say that order, those 5 cards, you can still have them in any order in your hand itself, but it will go ace, king, queen, jack, 10, and that will be the ultimate hand, okay? And we're going to include the royal flush as part of the straight flushes, but when we do the calculations of our flushes here, some of those straight flushes will be in this number here as well. So what I'm going to do is I'm going to go ahead and I'm going to first figure out the suit, and then I'm going to multiply by figuring out the face values of our suit. And so in this particular case, I know that there are only 4 suits available, and so I'm going to go 4C1. Yes, that is the same as multiplying by, that's going to be 4. But then I only have to look at my face values. I know my face values are 13, and I have to choose 5 different ones. Order of them does not matter. So the math of this is going to be 4C1 times 13C5. And at this point, I trust that you know how to type this into the calculator, so I'm just going to start writing down the final results. And we found out there were 5,148 total flushes. Again, okay, this is going to include straight flushes. Let's go ahead and figure out what a straight flush is. So again, I'm not going to keep writing determine. We're just going to assume. I'm going to have to figure out what the suit is first. Then I'm going to need to figure out what the high card of this is. And the reason I need to find the high card is in the other 4 cards, 4 high card face value, let me say it that way. The other four other face values will be predetermined at that point. So let's just say I've decided that I'm going to have 7 be my highest face value. Well, if that's going to be my highest face value, then I know I have to have a 6, and I know I have to have a 5, and I know I have to have a 4, and I know I have to have a 3. Therefore, I really only have one choice for those cards. It's going to be 6, 5, 4, 3. Don't, because if I said 7 is this and it's a straight, it's just the way it is. And so now I also have to figure out what are all my possible high cards. Well, I can have an ace, it'd be my high one. I can have a king, queen, jack, 10, 9, 8, 7, 6, and I can go as low as a 5. But I can't go any lower than that, because if I go lower than a 5, let's say I choose 4 as my highest face value, then it would have to be a 3, a 2. I can put the ace, but what do I put under the ace? Remember, you can't have ace be higher than a king and lower than 2 at the same time. But if I have a 5, I can make my ace the lowest card. So when I build my straight flush here, and I do my suit, it's still going to, and I do my high card, let's just say high card face value. The math for this is going to be 4C1. The high card face value, there's only 10 options I can choose from, 10C1, and so that means I will have 40 straight flushes. And of those 40 straight flushes, 4 of those will be the royal flush, because I only have one card that I can have as my top card for a royal flush, the ace, because that has to be followed by king, queen, jack 10. So there are 4 royal flushes. There are 36 straight flushes once I subtract the 4 from the 40. And then I'm going to take the 40 here and subtract all that from the 5148. And so technically there are 5,108, let's say, regular flushes. All right. And that's kind of how we do it. And that's why a flush is a very valuable hand. You can even if it's not a straight flush, when you only have 5,148 flushes total, or 5,108 just general flushes, out of 2,598,960, the probability of that actually happening, and again, we're going to include all flushes. Okay, we're going to include all flushes, even though it's 5180. You're looking at less than 0.2% that happening with just 5 cards. So a flush is a very valuable hand. But is it stronger than a 4 of a kind? Let's go find out. So if I was trying to build a 4 of a kind, here's where it gets kind of interesting. I would want to figure out 2 face values. And it would be where order matters. And I'm going to explain why I'm saying it this way. One of the face values, the first one, is going to represent my 4 of a kind. The second face value is going to be the one single face value that doesn't match the 4 of a kind. So order does matter, because if I go 6, 6, 6, 6, and then 7, that is not going to be the same hand if I go 7, 7, 7, 7, and then go 6. So we are going to actually need order matters, which means permutation is what's going to be necessary here. And so I think what I'm going to do now is I'm going to kind of do the math immediately and show you steps. So step number 1, it's 13p2. Then what I'm going to do is technically I should find the suits of the 4 cards that are 4 of a kind. The problem is, okay, that's going to just be 1. So here it is. I'll say suits of 4 of kind. But you're going to find out that really wasn't a very helpful piece of information. Okay, so I'll say suits 4 of kind, because there are 4 suits and I'm taking all 4. Order does not matter how I choose them. It's a group. And we know that 4C4 ends up being 1. So I really didn't need to write that down, but because we're trying to learn how to build a hand, I think we do need to write that down. And then I'm going to need a suit of my essentially 1 of a kind. And for that, I'm going to need suit, let's write that looks suit 1 of kind, and for that I will multiply by 4C1. And so when I do 13p2 times 4c4 times 4c1, now I know 4c4 happens to be 1, I know 4c4 happens to be 4. 13p2, I'd have to figure that out, but you find out that there's actually only 624 poker hands that will work out to be a 4 of a kind, which makes this even rarer than a flush. So yes, if you get a 4 of a kind, you should definitely be feeling that you're in a very strategic place to win the game, because it is becoming significantly harder. 624 divided by 2,598,960 now puts us in a number that is 0.00024, 0.02%. So if I'm going to do 2 pairs, I have to treat this a little differently than here. Here I needed to have order matter between my 2 face values, because I had to make sure that 4 6s and 1 7 didn't mean the same as 4 7s and 1 6. If I'm going to choose 3 face values, the problem is I have to actually choose 2 of them first, because I need to choose the 8s and the 3s. But the key is, since it's a pair of each and they have the same number, would it have made a difference if I would have put the 3s before the 8s? And the answer is no. I mean, in terms of ranking, we would say the 8s are higher, but in terms of the actual hand itself, 2 8s followed by 2 3s is still going to be the same as 2 3s followed by 2 8s. So when I choose my two face values, I'm going to abbreviate this with FV, order does not matter. And that means when I do my face values, which I'm going to write here, two face values, okay, for the pairs, I'm going to go 13C2. Now this will choose those, and then I can focus on that one card separately. But before we get to that card, I'm going to call this 1A. And I probably could have called some of these other 1As and Bs, but I didn't, and I'm not going to worry about it. Because what I have to do now is, all right, so I've chosen my 8s. What do I have to do? I have to choose my suits for each pair. But here, order does not matter as well, and I have to reset my suits when I get to my second pair, because I could have gone hearts, clubs, and then I could have gone again, clubs, hearts. But it could have been hearts, clubs. It wouldn't have made a difference because that order doesn't matter. But I have to do a reset because I have to be able to choose from all four the second time. So when I do the math and I go suit, and we'll say first pair, I'll go 4C2, but then I'm going to do it again and say suit second pair, and I'm going to go 4C2 as well. Now I've taken care of those four cards. Now I can just focus on the last card, which is kind of interesting because I could break it up into two ways. I could say, first pick the face value. Okay, I could say pick the face value from 11 face values. Because again, once I can't have it being an 8 or a 3, I have to eliminate all the 8s and 3s at this point, otherwise it's not two pairs. It might be a full house, which we'll talk about in a moment. And then I would need 2A, I would need a suit for that one card, suit for the one face value. And I could do this as two separate parts right here. I could say here's my one face value and here's my one suit. I could say it was 11C1 and 4C1, but I could have also merged this together if I wanted to, and just realize once I pick my two pairs, there's only 44 cards total. That's the 11 face values and their 4 suits, and I could have just rewritten this as 44C1. Well, that's, when you do the math for this, this works out to be, and I'm going to scoot this over now that I know I have enough room for this. Let's put that right there. I can find out that there are actually 123,552 different types of two-pair hands. So it's not a huge number, but it's significantly more than flushes and four-of-a-kinds. So now we're going to finally get to our last problem, which is the full house. And I would kind of know, is a full house better than a flush? Is it better than a four-of-a-kind? Is it better than a two-pair? Where is it? And so here we go. I need to pick my three-of-a-kind and my two-of-a-kind. And so that's where I'm going to kind of go back to my four-of-a-kind, because it did make a difference if I had 6, 6, 6, 6, and 7. I know I repeated that. But I want to make sure understood here that 22299 is not going to be the same type of hand if you go 99922. So when I pick my two face values, the order is going to matter, because I'm going to need to make sure I put them in order where one represents the three-of-a-kind and the other one represents the pair. So when I do my two face values, okay, but again, it's not 13C2, it's 13P2. Then it's simply suit of the three-of-a-kind, and then the other one is going to be suits for the two-of-a-kind or the pair. And And so the math for this is going to simply go multiply by suit 3 of kind times suit 2 of kind. Sorry for this kind of lousy handwriting, but that's why you're getting the kind of documentation on this. 13P2 is going to be multiplied by 4C3 and then followed by 4C2. Again, I have to reset, especially here, because if I choose 3 suits, I'll only have 1 suit remaining for 2 cards. That just makes no sense. And so I just reset. So 13P2 times 4C3 times 4C2 works out to be 3,744 possibilities. So you can see that your best hands are the straight flushes, followed by a 4 of a kind, then comes the full house, then comes the flush. So that concludes the multiplication counting principle lesson.